Okay, so this is my second talk, which is going to be about the general dispatch mechanism that I've been putting into MoarVM, and I hope you're looking forward to seeing code in multiple different languages during this talk. Yeah, we're going to be having a nice dig all the way down into the runtime today. So this is what I'm going to cover. First of all, you might be thinking, what on earth is dispatch? What is a dispatcher? Why do we care? So let's start there. Then I'll talk about the current approach that is taken and the sort of shortcomings and limitations of that. And then I'll talk about the new approach that we're taking to dispatch and implementing lots of Raku features which fall under the heading of dispatch. I'll then show some current results and talk about the current status and how long until this is shipped, and some future opportunities for improvements as well. So, what even is this? What is dispatch? Dispatch is kind of the thing that's everywhere and nowhere. So, if I have an object and I call a method on it, somehow we end up running the appropriate method. And this all feels pretty natural in a way, but there's actually quite a bit of mechanics that might be going on to make that happen, particularly in a language where we can do custom meta programming and actually customize what method lookup means. Multiple dispatch is also everywhere in Raku. When you add two numbers together, we don't, at least in the abstract, know the types of the two things that we're adding. And so we have to do a multiple dispatch. So the types of all the arguments work. And then we end up in the appropriate candidate. And that's an even more involved process than method dispatch. And of course, we have multi-methods, which means that we have the two of them together. So dispatch is really the thing that sits between the places in our code. It's how we get from place to place, and we kind of, despite it being everywhere, prefer not to actually see it. Especially, we don't like it when we're writing code that is doing the work, and then we profile, and then we discover that actually the runtime is spending a lot of its time figuring out where on earth to go in order to run the code, and that can sometimes happen. Particularly if you do multi-dispatches today with lots of where clauses and things like that, you can quite easily find that a lot of the runtime is spent effectively on dispatch, on figuring out which candidates to run, and it can be pretty high. Actually, though, I've come to realize that while there's things that we traditionally would call dispatch, like method dispatch, multiple dispatch, and so forth, really, you can see it in a very general sense. Dispatch is any process where we have a bunch of arguments and we consider the types or maybe even values of some of them, and that leads to a decision about what code we run. And that's incredibly general. And the nice thing is that if we actually embrace that genericity, we can come up with a mechanism that solves a lot of different kinds of dispatch problems. So assignment is a dispatch. We don't really maybe even think about it as one always, but it is. And what an assignment does is actually very, very variable. Pun intended, not intended, but it was good. Okay, so the first example here, we have an untyped scalar. And a scalar is an object, it has a value attribute. And when you do an assignment, it's just binding into that value attribute. If it's an untyped scalar, that's all we need to do. If it's typed, however, the behavior is a bit different. We need to do a type check on the thing that we're assigning. If we assign nil, it's different again. It doesn't matter whether the container is typed or untyped or defaulted. We need to find that default and reset it back to that, and the nil itself is discarded. And if we have a hash and the hash doesn't contain that key yet, then we need to vivify it. That's a lot of different things going on. interestingly, of course, in any given assignment that we look at in the program, it's probably only doing one of these most of the time. It's quite unusual to end up with actual polymorphism here, but it's still there's a lot of semantics there, and the decision is all based on the arguments to the dispatch. In fact, I went through and tried to make a list of things in Raku that are dispatch, and I suspect this is incomplete, but there's actually quite a lot of things in here. So there's lots of different types of method call. There's the normal ones, the maybe method calls, the qualified method calls in a role, normally when you want to say which role's method to go to solve a conflict. We have multiple dispatch, which is incredibly involved. We have the call same and next with, which means go to the next candidate of the dispatch, which is actually very context sensitive because it depends what sort of dispatch we're doing. We have wraps, which we wrap some code around something and then we have to move through those. Coercions have to decide what kind of coercion thing to call. We have return type and bind type assertions. You might think, is return type checking really a dispatch? And the answer is yes, it is, because in the case where it's successful, it's the identity function. In the case where it's wrong, then it's something that throws an exception. So all of these things are really cases of dispatch, where we make a decision primarily based on arguments and types, and they intersect. So you might have a call to a method, and you call a multi-candidate, and that particular multi-candidate has been wrapped, and then you do a call same, and you'll probably go through the wrappers, and then the multi-candidates, and then the methods. So the amount of semantics in this is mildly terrifying, and I've actually spent the last months dealing with all of them. So how have we tackled this to date? And what are the problems with that, and why have I made this the thing that I've been concentrating on for the better part of the last year, on and off? Well, let's go back all the way to the beginning, and not really the beginning of Raku, but at least the beginning of MoarVM. And MoarVM is the virtual machine that Raku is mostly ran on these days. And when I started out MoarVM, it was something that looked a lot like this. It was we might say, a naive interpreter of bytecode. And you have this is macroed all over the place. So it's C, but it's good at disguising itself. It's done like this because some compilers can do computed goto and some don't. Don't worry about that. But the principle here is that we basically branch over the instruction that we're meant to execute. We execute it. MoarVM is a register machine, so if you look at that add I instruction there, then it puts into the target register the result of adding the values from two source registers. And you can see we have conditionals, which if they have a bytecode position, when the condition is successful, then we jump to that location, and so on and so forth. So of course you have a lot of overhead there for dispatching each operand. And so when you're at this point, and this is how we started, you say, well, interpreting bytecode is pretty slow, but C is pretty darn fast. So obviously the thing that we should do is write the performance critical parts in C. So you look at the things that are really, really common, and you write C code for them. So you end up with some quite complex ops. For example, there's a find method op in MoarVM today, and it's implemented like this. It retrieves the object, it retrieves the register that we're going to put the found method in, it takes a method name, and it goes to find it. Now, first thing it tries is to look the method up in a cache. And the cache is actually in the current implementation pre-computed. It's just a huge hash of all the methods on that type, including the ones from the base classes. And if that doesn't work out, then it actually has to call the find method on the meta object. And if you think about that, that means that to find a method, we might actually also have to find a method. And there's a nasty little restriction in MoarVM today, which I don't think anyone has managed to run into yet. But someone will probably correct me on that. That if you do a find method and then you have a meta object, that meta object's find method has to be in the cache. I'm getting really confused trying to even say this. And it gets worse, because if we call a find method to find a method, that can be written in Raku. So the whole process of doing the method lookup is actually, there's some stages there. And when you start doing these things, and you're in a virtual machine that has to support continuations, which is the magic between gather take and await async, you end up having to write C code in continuation passing style. And that is just like the thing in JavaScript or Node.js before they had async await, where everything is callbacks everywhere. And so an amount of MoarVM ended up looking like that. And it's even more fun when you don't have garbage collection. And it's even more fun when you're in MoarVM and you have garbage collection, but only for some of the things, and you have to be really careful which ones. I think I might have convinced you that this is kind of complex and not necessarily in a way that is conducive to being reliable and robust. Of course, we put a lot of engineering into this, so it is pretty fine, but it's kind of tricky. Booleanification. So if every time you do an if in Raku and we don't know it's a native type, this opcode in the bytecode interpreter is what interprets it, and it calls this thing called isTrue. And the reason that we do this is because in a lot of common cases, we really want to try and avoid calling the bool method, because method calls could be pretty expensive. So we sort of have a switch statement here which tries to work out what sort of type it is, and if it's some kind of special type it can cheat on, rather than actually calling the bool method on it. And you might say, well, it's another switch statement to decide what to do, but it's C, so it's fast, and it's faster than the whole bytecode interpreting, and it's definitely faster than method calls. So this seems an okay trade-off. And all of this made sense in, I guess, 2013. With time, it's started to make less and less sense. And that's because MoarVM has been learning. It's a very different machine than it was when it started out. It can do all of these things. It can do type specialization. So when it interprets a program, it looks at what types really show up, and then it produces optimized versions of the program for those. So it doesn't just run your code, it actually rewrites your code for the situation that really occurs. And it can even do that speculatively. So if it says, the statistics say that 99% of the time this thing is an int, it can optimize the code for that case. And if it goes wrong, it can say, well, it went wrong, so let's undo all the optimization and fall back to running the original code. So behind the scenes, the virtual machine is actually flipping between optimized and unoptimized, potentially thousands and thousands of times a second. We of course prefer it to stay in the optimized ones, but it's actually strategic to leave slow paths out of optimized code sometimes. Inlining. So we copy small routines into the routines that call them. So all those bool methods which don't do a lot, we can get rid of all the calling overhead of them. This is really important in Raku because even adding two numbers together is a multiple dispatch. If you actually go and do all the calculation and you do all of the calls to those, it's really, really slow. So we rely heavily on these sorts of things. And then that interpreter, which does the whole the switch statement thing, or the computed go to, we can get rid of that overhead because we can convert the bytecode into machine code, and then the CPU just chokes through it. These things change everything. At first we only had a bytecode interpreter, but now we can JIT compile it into machine code. Before, lots of little method calls were really expensive, and you did some tricks to avoid them. But now we can just inline them, and the cost is kind of gone. And that in the past, doing the hot things in C was kind of a clear win. But nowadays it's really not, because the C code is just this opaque blob of stuff that we can't see inside, and so we can't use all the type information that we've gathered to optimize. It's actually worse for us that things are in C for fastpaths now. That doesn't mean it was a mistake to build the VM that way in the first place. We didn't immediately go and have the budget to go and build a VM doing all of these different things, but with time we have built them, and we're in a very different place. One of the other things is that only some kinds of dispatch got special treatment in the runtime. This is actually a really nice place. This is where I'm going on vacation next week, and the reason that I put it in here is not just to make me happy thinking about that, but actually because I want to talk about performance cliffs. And a performance cliff is something where we have a bunch of things that are pretty fast, and we write programs using them, and then we have some other language features, and if we use them, we fall off the performance cliff, and suddenly things are really, really very slow indeed. And yeah, this is a partial list of course of these things, but if you just do simple multiple dispatches, or you do method calls, or you put things in Boolean contexts, this is all decently fast today. But if you do a multi-dispatch and you data write a where clause, or you decide to use call same, that is a real huge slowdown today. The qualified method calls and maybe method calls used to be the same kind of painful. They're actually somewhat better now in master because of an intermediate solution on the way to the new mechanism that I'm talking about today. But they're still not really ideal. And the sort of rule here is that if you have something that's a dispatch, and the runtime, the virtual machine, and especially its optimizer, doesn't really understand it as a dispatch, it's probably going to be really slow. And you might say, why is that? And really, it's because there's a lot of costs that are there, but they're not immediately obvious. If we implement the maybe method call like this is the original implementation of the dot question mark operator. It actually compiled into a call like this one below. It called this dispatch dot question mark method. It passed the invocant, it passed the method name, and then the rest of the arguments were slurped up. And then it checked if the method was there. It called the method, and you kind of look at that and like, well, there's some costs in there, but what makes it really bad? And the thing that really hurts in an optimizing virtual machine like MoarVM is that it turns what I call mild polymorphism into megamorphism. What do I mean by that? Well, this is a measure of how many different places might this call go. So at a given location in the program, logically that dot question mark, depending on the type of object, in the really lucky case, we always get the same type there, and it always either has the method or doesn't have the method. We call that monomorphic because there's only one possible destination. If it just goes to a few different places, we'd say that's polymorphic. So sometimes the method is there, sometimes it's a type where it's not. And then there's this situation called megamorphism. And megamorphism means that there's loads and loads of possible places that it could go. Now, when you're specializing code for particular types, monomorphic or likely polymorphic things play really well with that, because you produce a version of this code at the top, which is compiled for a particular type, and that type either always has the method or never has the method. And so you end up being able to completely eliminate the check of if the method is there, and maybe even inline it, or just turn it into nil if it's not there, and then there's no call at all, it's just a constant. But if you have some point in the program like this below where they all congregate and all of the calls end up there, it ends up megamorphic, and there's not really much we can do about that. So, one name, handful of types, many names, many types, very, very different situation for the optimizer. And every time that we don't really have a mechanism to express the dispatch to the runtime, we end up in that second situation, and it ends up not being able to do a very good job of the optimization for us. So really, optimization is very heavily reliant on turning potentially polymorphic programs into mostly monomorphic programs. Now, of course, there's an even worse thing here, which is that we slurp all of the things there, we flatten them there. That's also pretty slow. So yeah, this is a lost opportunity as well. Actually, in current Rakudo, if you call something with flattening arguments, a whole bunch of caching of dispatch lookups and things don't really work out, and you lose a bunch of performance on that too. So there's so many reasons why that's bad. So what can we do about this? And one thing you might think is, well, let's just teach the virtual machine about more language features, and then it will do a better job at all of them. But it's not that easy. We already know that we're beyond the point where writing hot path code in a C function is not actually going to help us. The type specializer can't see into it, so it really wants to see bytecode and inline caches and other things that it can talk about. The other thing is that it's actually really hard to write these things correctly in C once they get complicated. And a bunch of the orchestration of dispatches in Raku are really very complicated indeed. Yeah, it's only a small slip up to get a garbage collection bug or something into there. So I really would like to be writing a lot less C to actually make these things faster. The other thing is that if we want to have new language features and they involve some kind of dispatch, modifying the VM is quite a restrictive way to do it in terms of who has the background to do so. Whereas if we have something that's a little bit more general that we can configure and tell about new dispatches, then in theory it's much easier to get new features in and get them performant. So I've adopted a more sort of generalized approach now. We have one new instruction. It's called dispatch. It's exposed like all of the other virtual machine ops. We expose them via an NQP : syntax. You can't write this directly in your Raku programs without the pragma, but this is a call down to something provided by the runtime. So here are two examples of using this. So the dispatch op takes a dispatcher ID and 0 or more arguments. And you might be looking at this and saying, congrats, Jonathan, after all these years, you've learned to implement the identity function. And yeah, they look rather like that. But actually, if we write this, then we can see a difference. So here I am using the new dispatch mechanism. I'm calling a dispatcher with the name boot value. I'm giving it an argument. And then I'm calling another dispatcher called boot constant and giving it an argument. And we can see that boot value really is the identity function, and boot constant is something that just remembers the first value that it saw and always evaluates to that in the future, regardless of the thing that it's given. So you might think, huh, there's some kind of cache going on here. How does this actually work? And to find that out, we'll take a look at the bytecode. And the bytecode is essentially the assembly of the MoarVM virtual machine, and it looks like this. And the things to spot in here are the two dispatch ops. But actually, if we look closely at that, we'll notice that there's other dispatch things as well. There's this one here, which corresponds to calling the save function. That is a lang call dispatch. And this is NQP code, the small restricted Raku subset we use to implement the compiler. And the concatenation operator here needs to turn values into strings, and that also now is done using a dispatch. And the dispatcher there is called NQP stringify. It would look like we've been kind of successful in making the dispatch mechanism general, because apparently half of the program now is dispatch ops. Now, what actually happens when the virtual machine sees these? Well, the very first time we run this function, it goes through a process called bytecode validation, where it checks there's no like go-tos out of bounds or any other weird invalid things. And for every dispatch op, it allocates a piece of storage. And into that storage, it sets a pointer to a singleton object, which is an unlinked state. When we run the dispatch op, it does this. And don't worry about all the details of this, but we'll walk through the steps. First, it finds the location of the current state. And by the current state, I mean the slot that we allocated for the dispatch instruction. It then says, okay, what is the current state? So it dereferences it to see what sort of result we have there now. We then look up the ID of the dispatcher, what sort of dispatch we're doing. We look up the call site, which is the tells us about the number of arguments that are getting passed and if any of them are named arguments. We locate the arguments to the dispatch. We do a bunch of setup work for the return value. Don't worry about that. And then the really important piece is here. That's the ICE, which is short for inline cache entry. Is then run. We have a run dispatch function on it, and this does whatever the right thing is. Now, the right thing in the unlinked state is to record a dispatch program. So when we do this, we have the boot value is one of the things built into the virtual machine, and it produces a little program like this. And it says load argument 0 into temporary 0, and then set the result value from that temporary. So basically just copy the input into the output. Boot constant looks a bit different. It says, well, we have a table of constants with this program. Just load the first one, the 0th one here, and then use that as the result. Boot constant and boot value are two things that I call dispatch terminals. They're things that produce a final outcome, whether that's handing back a result or, as we'll see in a moment, running some code. So this is another dispatch terminal. This is the way, with the new dispatch mechanism, that we actually make bytecode run. We call boot code, we give it the piece of code, and we give it the arguments. And again, this is the way that we're running things. There's another one called boot syscall. Boot syscall is calling functionality built in to the virtual machine. So there's a built-in called LMs, which gets the number of elements in an array, and we can just call that using the syscall mechanism. That's another terminal, another thing that results in an action being taken. It turns out that these 4 are enough for everything. Basically, produce a value based upon an input, produce a value and it's a constant, run some bytecode, or run something built into the VM. Everything else that is built on top of this is built as something in terms of these four. And that pleases me, because we've got something at the core that's fairly small. I see someone asked a question, which then disappeared. Okay, I'll answer the question later. Well, I don't know how Zoom works. Okay, so that's all we need. So then you might say, but that's a pretty big gap from doing all of the fancy semantics of the Raku language. So all of the fancy stuff happens because we can declare dispatchers in what I call Userspace. And by this I mean dispatchers that we write using a high-level language, and they're all at the moment implemented using NQP. So you use the boot syscall mechanism to register a new dispatcher. I'm calling this one identity for reasons that will become obvious very soon. And this gets invoked with a capture object, which represents the arguments to the dispatch. Every user-defined dispatcher should ultimately delegate to some other dispatcher. And in this case, I'm just going to delegate to boot value. So you can see I'm doing a boot syscall. I'm saying the syscall is dispatcher delegate. Then it has boot value there, which is the name of the dispatcher I want to delegate to next. And I'm just passing the capture along. And boot value is the identity function. So all I've done here is wrapped up the identity function in another dispatcher. And yeah, that's not very useful yet. That's how we call it, by the way. So if you do an NQP dispatch after registering this, we can already use that dispatcher straight away. Here's where things get more interesting. We can do transforms on the capture. So for example, if you look at the bottom of this first, I have a dispatch to drop first, and I'm passing the code. I'm passing a 1 and a 2. And that piece of code takes only one argument. In the dispatcher, we take the capture, and we say dispatcher drop arg, and we get another capture back, which represents the original one, but with argument number 1 missing. Remember, argument 0 is the code to run, and argument 2 is, in this case, the number 2. And then we delegate to boot code, and we end up with the invocation. What about this one? So this is called type name. This is a dispatcher that will map a type, well, an object, into the name of its type. So this is a little bit more involved. That NQP capture possarg extracts the argument value from the capture. And then we are going to ask for its name. And then we're going to take our call site and we're going to insert a literal string as the 0th argument. And then we will delegate to boot constant. Now, boot constant ignores everything except the first argument. Boot value does as well. So inserting something at 0, it just means throw away the rest if we give it to one of these two. So we've got something which hands back type name. Does it work? No. And what happens in here is we call try it, we pass in the badger. In here, it gets the badger, it gets the type name, it inserts the string badger, and it sets it as a constant. That is the recorded dispatch program. The next time we hit it, we say, we already have a dispatch program here. So we run it and we produce badger. And yeah, we never get our mushroom out. And that's a problem. So how do we fix that? Well, the other important piece of dispatchers is guards. And here we take the capture, we say, I want to track the 0th argument, and then we send it into a guard function. And what this means is this dispatch program is only valid if the type matches the one we observed when recording it. And that is enough to fix it. Now, you might be looking at this thinking, this all looks very expensive because we're dealing with all these captures and we're inserting guards, we're delegating between dispatchers. But when we end up with the final dispatch program that we actually install at the call site, despite all of that going on and shuffling around of things, the dispatch program erases it all. There's no trace left of the delegation. There's no trace left of all the intermediate capture objects and tracking objects. It's just a free instruction dispatch program, which is check that the type is badger. If it is, grab the constant from the constant table and use it as the result. So what's happening with the call site is it starts in the unlinked state. We record the dispatch program and it moves to the monomorphic state. And for the next calls where we pass in a badger, it stays there. Then when we pass in the mushroom, it records another dispatch program. And then the state moves to polymorphic, which means there's a list of different dispatch programs that we all consider one by one until we see the matching one. This is a real example, and I won't go into every little detail of it, but this is how NQP resolves method calls. So we try to find the method. So we're just extracting the invocant, the first argument. We're finding the method name, and we're calling find method. And by the way, that restriction I mentioned before with caching the find method is all gone now. If there's a method, we say, well, it's only valid to assume this is the method result if the type is the one we saw and the method name is the one we saw. Because most method names are actually constants. So you know that check is free. It can see that it doesn't need to do that. We tell it to do it in case it's a method dispatch that depends on the name, but most of the time that ends up as a free check. And then we say, okay, take away the method name and invocant, insert the resolved method, and then delegate to something which will actually invoke it. And that thing is called lang call. And the reason is that this might be an NQP object, but they can get subclassed in Raku, and we need to do the right thing, depending on the type of code it is. Everything else is built out of these building blocks. So in Raku, we have a similar one. The only big difference in Raku is that we support resumption. And resumption is the thing behind call same and next with and going faster with multis with where. And the idea is that when we do a dispatch, we can indicate what information we might need later on. So when we call a method, we can say, well, originally we had this type and this name, and we might need them later. In the best case, there's zero runtime cost for that. That's actually the common case. There's no cost for that at all. It's only if we actually use call same that we go back and say, well, we need to know what the original method and the original arguments were, so we can figure out what method to go to next. And that is how we end up being able to do much better at those features. How the resumption works is a talk in itself, so yeah, we won't go there today. Now, where this then gets really interesting is that dispatch programs that we've recorded and put at a call site are available to the optimizer. And the optimizer can look at them and it can say, well, now I know where this program tends to go at this point. And then it can do all of the nice things that it knows how to do. It can inline things. It can say, oh, I already proved that this thing is this type earlier by doing data flow analysis, so I can throw away this type check. And once it's got rid of probably quite a few pieces of this, it says, oh, okay, we'll JIT compile what remains and get rid of the interpretation overhead of the program and also of these little dispatch programs. So all of this is actually carefully engineered so that it is giving the optimizer exactly the sorts of things that it wants in order to do a good job. So the question is, how good a job is any of this doing? Well, first of all, this is very much something that's been a very active work in progress of late. As of a few weeks ago, this number would have been a lot smaller. But at the moment, the new dispatcher with Raku running on it passes 99.6% of the test suite. That's pretty close. We're down to, like, you can count the failures on your fingers. We've got about 40 ecosystem modules that we need to have a look at to figure out why we might have regressed those. So in terms of it being correct, it's doing pretty well. What is still in progress is getting it all reintegrated back into the optimizers, so that it uses all of this information to do the optimizations. And quite a bit of that is still to go. So a lot is done, but there's a few really important bits missing. So for cases like method dispatch and multi-dispatch, at the moment it's actually slower because we haven't reinstated those bits yet. What we could sort of measure though is, well, there's two things. The first one is, what happens if we disable the optimizer? Is it competitive then? And the answer is yes. This first one, method calls, is just a loop doing method calls. Now, if the optimizer knows about this, and once the optimizer knows about this, it actually turns it into an empty loop. At the moment, that doesn't happen. If we disable the optimizer, though, we can see that it's actually a little bit faster at doing this empty method calls. The one that surprised me a bit was this one, the multiple dispatch result, because we've actually gone from using a cache that was specially implemented for multiple dispatches to using a completely general purpose mechanism for all dispatches, and we still win anyway. I'm pleased about this. I'm also slightly, surprised that this has immediately been achieved when there's still things that we can do. That's competitive, but there's actually still more to go in terms of improving the baseline even before all the optimizer stuff kicks in. Baseline, by the way, is sort of important because while it's true that optimizing the hot parts of the program is really important for performance, getting through the cold parts that you only run a few times quicker is also quite good as well, especially at startup time. And yeah, as I mentioned, this is a result that was a bit better than I expected. So I'm relieved about that one. The other thing that we might ask is, well, UDisp was aimed at trying to speed up a bunch of things that are really bad on the master wrench. Is the new design good enough that even without the complete optimizer integration, it can show an improvement already? So if we run some benchmarks with UDisp not completed with the optimizer, and we run Raku master with the optimizer doing as good a job as it can, who will win? And the answer for the three things I tested is UDisp, and already by quite a margin. So this first example is a multiple dispatch to a where clause. And yeah, it's a factor of 3, maybe 4 already. And that is going to improve further. I mean, it's not actually succeeding at inlining that multiplication operator on UDisp at the moment. Once it does, that will be a huge improvement already over what it's doing now. In fact, probably all of this can get inlined, both of the calls eventually. this is just doing loads of call sames. Call same is really very costly on master, to the point that you, in places where you might use it, you sort of avoid it if you can. You might say, I don't use call same in my code. How does this help me? The answer is that a lot of things actually use it behind the scenes. If you're using Crow depends on a module called OOmonitors. OOmonitors uses call same. Call me also on master goes through some amount of contortions. In newdisp, we just basically rewrite the dispatch to call that method instead. And this one, when we're fully set up with the optimizer, will just turn into an empty loop as well. So yeah, there's some work to go before we merge this back, and these ones are all coming out much better, which is nice because this is the one of the primary goals was to improve the performance of these kinds of features. There's a few future opportunities for improvement. Of course, the first thing is get it good enough to merge. So this isn't going to happen in August, primarily because I'm going on holiday tomorrow for 2 weeks. But I'm kind of optimistic that we might land this in September. So that would be nice. Once we've shipped it, there's more to do. So in the initial merge we do, dispatch resumptions will not be something that we especially teach the optimizer about. But we'll get there. When we do, then we might start getting to a point where you can write your factorial with where clauses, and it's kind of competitive with just writing it with conditions. Call same, the same kind of story. One other thing that would be really good to integrate with this as well is native calling, because that will get all of our various bindings for databases and other C libraries to be much more performant as well. At the moment, there's various bits of transformations that go on before we actually hit the point of doing the C call, and those could mostly be expressed as dispatch programs. And then if we have a new dispatch terminal, which invokes a C function using native call, that should in theory be quite a lot faster. And then we can get the JIT compiler involved, and I think we can finally realize the goal of having the JIT compiler basically read directly out of MoarVM registers and call the C function straight in line without any messing around. So that could maybe be a really nice improvement too. And there's lots more. There's lots of little things which today are not so performant that we can tweak and get going a lot faster with the new dispatcher. We might also be able to expose some things we don't have today. Crow request routing today actually checks the signature of a root will match and then invokes it. And there's not a reliable way to just invoke it and find out if it was the thing that failed. And yeah, we can actually maybe expose a call if it binds and enjoy faster request routing there as well in the future, and for anything else that does that kind of design pattern. So I have easily used up all of my time. So I'm not really sure I have time for questions. I see. Vadim commented, at some point MoarVM will try to optimize dispatching programs. The thing is that actually, yes, because you make all of these boot sys calls, it already actually is optimizing the things that produce the dispatch programs. So yeah, that's way ahead. And yep, there's no more time. So thank you very much. Sorry for going a little bit over. And I wish you to enjoy the lightning talk.